All right, I'll go ahead and get started here. Before we broke for lunch, we heard a little bit about what's going on with contemporary recruitment dynamics for Cisco and Lake Superior, and a little bit about population declines. Again, this is all contemporary stuff. My talk's going to focus more on historical things that were going on prior to collapse in the 1950s. So if we take a look at a graph of yield here, we have millions of kilograms on the y-axis and then year on the x-axis. And we see that historically, Cisco were the predominant prey of most fish predators and targeted commercial fisheries in Lake Superior. And they accounted for an average of about 5.4 million kilograms per year during 1912 to 1962. Stock size declined steadily thereafter in 1962, and fishery yield really hasn't recovered since then. Stock size remained low until recruitment, and resulting adult stock size increased during the early 1980s. The fishery yield has really stayed low, and this is primarily due to smaller, more regulated commercial fisheries. Now our historical fisheries, which would be roughly this black bar here, they were using bottom set gill nets to target pre-spawn fish for their flesh, and these were primarily used for animal food and human consumption. With our contemporary fishery, which is the bar you see here, we're using floating or suspended gill nets to target pre-spawn females for their roe. And these make up about 60 to 70% of monitored commercial catches in both Minnesota and Wisconsin. Now if we take a look at a figure that shows age 4 catch at Bayfield during the 1950s, we see that scale ages suggest that catches were dominated by age 4 fish and that recruitment was relatively constant throughout time. And if you look at the peaks of these bars, we're really looking at an average of about 50 to 60% of our commercial catch in Bayfield coming from age 4 fish. And there's really no variation throughout the entire decade. It's very similar. If we look at a comparable figure from our Sand Island spawning survey for the contemporary period, our otolith aging suggests that contemporary catchers are driven by highly sporadic recruitment. And then these very strong year classes, which we see here, and Dan and Corey talked about in the earlier talks, these really persist in the fishery for 20 plus years. So again, highly sporadic, and then everything that's driving the fishery are these strong year classes you see here. And then age 4 fish is making up a much smaller proportion of our commercial catch. So this brings us to our objectives, which are to determine whether historical Cisco yield in Lake Superior can be explained by contemporary life history and recruitment dynamics. And basically we're going to be asking the questions, can stocks that exhibit sporadic recruitment and 25-year longevity support historical levels of yield, or was historical yield sustained by higher adult density and more frequent recruitment than we're seeing today? And the main point of this exercise is to go back and look at the historical fishery a little bit closer and fill in a lot of knowledge gaps that we have at this particular point in time. And to do this, we're going to be using stochastic age-structured simulation models. Now these next few slides are going to be set up roughly the same. We have age class across the top going from 1 to 25, and then we have simulation year down the side going from 1 to 200. And throughout the model, we're going to be keeping track of age classes from 1 to 25, and then we're running our simulations for a total of 200 years. And then this middle portion of the model, which is blank now, is where we're going to populate our model with observed historical data or contemporary data for contemporary models. And we're using published data, and then we're also using agency records as well. So we're going through and we're populating the model, making sure everything's grounded in observational information. And as we're going through and doing this, we're maintaining random variability and stochastic error throughout all of these relationships. And the random variability incorporated in these relationships is calibrated to what we're actually seeing in the data. So the first step in this process is to determine an initial age structure in abundance. And to do this, we're using scale ages published by Dreyer and Beil in 1964. And these are back in their study for the 1950s across the whole southern shore of Lake Superior. And then we're converting these scale ages to otolith ages using a scale otolith conversion key. We have 847 paired scale otolith samples that were provided by the Wisconsin DNR, crack and burn only. And what we're doing for this portion of the project is we're fitting a skew normal distribution to each scale age, and then using that skew normal distribution to determine our otolith ages. When we do that, this is again an example from Bayfield. We start out with the gray bars, which are our scale ages. We run them through our scale otolith aging key, and then we end up with our white bars, which are our otolith ages. And these modeled otolith ages are what's going into the model for our initial age structure and abundance. And as you can see here, everything shifts the distribution for the ages to the right, but we still don't have any fish older than age 11, and this is in all units. And then only about 2.5% of fish are older than age 7. And this really goes back to the distribution of the scale ages that were caught in the commercial fishery back then. When fish are predominantly age 3, age 4, and age 5 on scale ages, it's typically a 1-to-1 or a very close to 1-to-1 relationship with otolith ages, so you just don't get very old fish based off of those scale ages. After we estimate our initial age structure and abundance, we need to forecast that age structure and abundance to the following year. And we do that using the equation you see here. And this incorporates natural mortality, or M, fishing mortality, or F, and then selectivity. And we take these parameters and we apply them to the population in the previous year to estimate our population in the following year. So if you think about the initial age structure and abundance box, what we're doing is we're shifting it over 1 year and then we're shifting it down 1 year. And this is how the model cycles through year after year following these equations. For our natural mortality, we're using the Pauli 1980 equation, which basically accounts for life history parameters and then temperatures occupied. For selectivity, we're using observed selectivity and gillnet catches. And then to estimate F, we're using catch curve analysis, where we estimate our total mortality and then subtract our natural mortality to get our fishing mortality, or F. After we estimate our age structure and abundance the following year, this is where we get to really the core of the model, which is our stock recruitment function. So for this particular species and this particular model, we're predicting age 1 recruitment for Cisco from the abundance of age 3+ recruits 2 years earlier, and we're using the Rook stock recruitment function here. This function incorporates a density independent parameter, alpha, which is basically the recruitment rate at low spawning stock size. Then we have a density dependent parameter, beta, which is basically the way the recruitment rate changes as adult spawning stock size increases. And then importantly, for what we want to look at in this study is this epsilon term, which is a basic descriptor of our random variation in the stock recruitment model. Now, as we're going through and building the model, we have observational data for basically everything else surrounding the stock recruitment function. What we don't know are alpha, beta, and epsilon, and this really gets to the core of, how do historical stocks compare to contemporary stocks. So as we're going through, we're basically taking and starting out with stock recruitment parameters which were previously published, and then we're calibrating these based on trial and error until we're actually mimicking our observed historical yields or our observed contemporary yields with our model yields. And when we do this, to estimate our yields, we're using the Baronoff catch equation, which incorporates fishing mortality and natural mortality, and then just applies that to abundance. And then we apply a weight function to get our yields in kilograms. And as we go through and do this, our simulations are going to be 1,000 iterations for 200 years each. And then the first 50 years of each simulation is a burn-off period. And then the last 150 years are what we're using to estimate summary statistics for the population under this stock recruitment relationship. And for summary statistics, we're looking at things like recruitment, yield, adult abundance, and then we're also looking at probability of collapse and then time to collapse. And in this particular presentation, we're defining probability of collapse as a drop below 10% of our initial starting adult abundance, meaning age 3 fish. We completed the historical modeling exercise for all 4 management units seen here, Duluth Superior, Wisconsin, MS3, and MS4. Everything roughly corresponds to the historical management units prior to when they were reorganized, except for the western arm of the lake. Those needed to be arranged a little bit differently due to the data that was available. And for the rest of the talk, I'm going to be focusing on results from Wisconsin, because this is where we do have a completed historical model and a completed contemporary model, and it serves as a really good compare and contrast situation. So the next few figures are going to look relatively similar. We have spawners on the x-axis rather, in millions of fish, and then we have age 1 recruits on the y-axis in millions of fish. Our contemporary model is down here towards the origin, and then our historical stock recruitment model is up here. The peaks of each of these curves represent where peak recruitment lies, and then the spawning stock size that would produce that peak recruitment. So you can kind of think of these as a rough compare and contrast of sort of a pseudo carrying capacity if you want to qualitatively compare them. So historically, our peak recruitment and the spawning stock size that produce peak recruitment are right here. Now they're right here. If we go in and we look at the parameters that were estimated in each of the Ricker models that go into these relationships, our alphas, which are the density independent parameter, which function really down close towards the origin, those were very similar, really no difference there. But as we get larger and larger adult stock sizes, our beta parameter kicks in, and we get more and more density dependence in the contemporary model. And if you look at the contemporary beta parameter, it's about 8-fold larger than the historical beta parameter, so there's about 8 times more density dependence occurring now than there was historically. So one of the things we need to do with these curves is go through and actually look at what are our acoustic estimates right now and compare them to the curves and what we're getting for our model estimates. In Wisconsin waters, acoustic estimates are really highly variable depending upon sampling strategy. Our summer estimates, which are this bar over towards the y-axis, are taken during summer when fish are spread out throughout the lake. They're very low density, so this leads to really low estimates of absolute abundance in any given area. Now our November acoustic estimates, which are right here, are taken during fall when fish are aggregated on spawning grounds. And these are highly dense pockets of fish, and these lead to relatively high estimates of total abundance. Now each of these bars represent the 95% confidence interval for each of these acoustic survey estimates. So we have our summer survey estimate here. Again, this is probably towards the low end of what's plausible and what's out there in the system now. And our November estimate was taken in 2006. So we had 2 very strong year classes that hadn't fully recruited to the fishery yet, but were still being recruited to the acoustic survey. So this is probably towards the high end of what's plausibly out there right now. There's probably a little less than this during the current time period. So if we take a look at what we're getting for our model estimates, our contemporary model, these are averages of 150 years, and then the 95% confidence intervals that go with those averages of 150 model years. So they're relatively compressed compared to what you would see if you looked at individual years. Our contemporary model falls right in between the 2 acoustic estimates. And if you were to expand this out based on individual years, these would be from about 5 million fish to 125 million fish. And then our historical model is the yellow bar or orange bar. And that falls towards the larger end of what we saw in our November 2006 acoustic estimate. There's some overlap there, but it's very close to what we saw on the top end of that. And if you expand those out to individual years, you see values ranging from about 40 million fish to 150 million fish for 95% confidence intervals. And one thing I want to point out with each of these bars here is that you can fit about 4 of these historical model bars into one of this contemporary model bar. And that really gets back at the epsilon term in the stock recruitment curve, which measures our variability in recruitment. And what we see when we compare that in terms of numbers is we see that our epsilon term, our variability in the stock recruitment curve for the contemporary model, is about 4 times what it was for the historical model. So if you want to sum everything up, much more density dependence for contemporary populations, and also much higher recruitment variability for contemporary populations. The good thing about this is when we do get strong year classes and strong recruitment events, those typically produce adult abundances, if you compare this gray bar to this orange bar, that are very similar to what we would have expected to see historically. We just don't get those very often. And I think in the system, everything, when we do have these large recruitment events, everything's going to sort of want to naturally migrate back to this peak. So that may be a position we're in right now, where we had large recruitment events that maintain themselves as adults through the system, and now everything is migrating back. So we have these smaller recruitment events now. One of the other things we're producing as far as model outputs go is probability of collapse under different exploitation rates. So if we take a look at this figure, we have exploitation rates ranging from 0 to 1 across the x-axis, and then we have probability of collapse on the y-axis. Now our exploitation rate is just the fraction of the adult population we're removing due to fishing every year. And then our probability of collapse is the number of our 1,000 iterations, or the proportion of our 1,000 iterations where the population does collapse below a certain point. And in this particular figure, it's 10% of our initial starting adult abundance. So in our historical model, which is the dashed line you see here, once we hit an exploitation rate of about 0.15 to 0.2, we start to see a sharp increase in our probability of collapse. And then in the contemporary model, once we hit an exploitation rate of about 0.4 to 0.45, that starts to increase as well. Now the differences between these two curves really go back to the differences in the life history parameters of the fish that were present in the time historically versus today. And they also go towards the differences of the commercial fishing gear that were used historically versus today. Now for our historical curve, we have a very small maximum size fast growing fish population, and they're being targeted with relatively small gill net meshes. So this results in a fish population that's targeted at a very young age, reaches full selectivity at a very young age, and then it stays fully selected throughout its life. With the contemporary population, they're targeted at a much later age, they reach full selectivity at a much later age, and they don't stay fully selected throughout their life. Now if we take a look at our estimated exploitation rates for both the historical and contemporary fishery, we see our historical fishery is right up here at about 0.53, which is not good, and this would be the late 50s. And if you take a look at graphs of effort for Wisconsin, once you correct them for changes in gill net materials, you see sort of this ramp up of effort through time. So this was about the maximum level of effort that was ever extended in Wisconsin. So basically doomed to collapse, at least for our definition of collapse right here. And then as far as the contemporary fishery goes, we're working with about 0.15 for an exploitation rate. And this looks relatively conservative based on this figure, and relatively sustainable, but again, this is based on the last 25 years of data, and that's how our stock recruitment curve is calibrated. So this includes recruitment events such as 1984, 1988, 1989, so very large recruitment events. If you go and you look at the recruitment data that's been occurring in the last 10 years and plug that in rather than what we're using for our calibrated stock recruitment curve, it paints a much different picture. It basically takes what we see for our contemporary curve and it would slide it this way and result in an adult population that's much more susceptible to collapse due to a lack of recruitment. Another statistic we're keeping track of as far as model outputs are median years to collapse. And this is just the number of years our model simulations go to is 200 here. In this particular case, a high number is good and then a low number is bad. And the idea here is we want to maintain a population for as long as possible and give ourselves as managers as much time as possible to make adjustments if we do see problems coming ahead in the future. And again, if we go to an exploitation rate of about 0.15 or 0.2, we start to see a sharp drop in time to collapse. And then over here about 0.4, 0.45 for the contemporary model. And then these are where our exploitation rates are estimated for both the historical and contemporary models. And this right here is exactly what we saw with the historical fishery in the 1950s, and just about the same amount of time it took to collapse that fishery in the 1950s. So to kind of sum everything up, historical yield cannot be explained by contemporary life history and recruitment dynamics. Following large recruitment events, we do see adult stocks that are large enough to produce more consistent yield and more consistent recruitment and support what we were taking out historically, but this isn't happening. One of the things that was interesting to come across going through some of the historical data and some of the contemporary data is that Cisco's now have a much greater fecundity, at least compared to the dry and bio study, than what we saw in the 1950s. And in theory, if all things were equal, this should be translating to a much higher reproductive rate and a much higher alpha. But what we're really seeing is a similar reproductive rate, regardless of the fecundity that's occurring. So with this, I think there's probably some sort of a compensatory mechanism working to kind of make up for years when we don't have recruitment. And I think the higher fecundity can probably explain some of what we're seeing for this high degree of variability as far as year class strengths, but it doesn't really explain the sporadic nature of recruitment. I think you have to look to environmental factors to explain the sporadic nature of recruitment, and also sort of our reduced carrying capacity that we're seeing as far as the peaks in the stock recruitment curves go. And this sporadic recruitment is really what's primarily going to be the limiting factor on parental stock size and resiliency of parental stocks, especially when you get towards higher exploitation rates. And our results agree with some previous studies as far as stock sizes being restored, but we disagree on the conclusion of recruitment being as variable as contemporary recruitment. So what we're seeing now is similar recruitment rate at low adult stock size, much greater density dependence, and then much greater variability in recruitment compared to historical models. And with that, I'll take any questions if we have time.